Welcome back, everybody. Today we'll be deriving the idea of the linear impulse momentum equation. So the very first thing I want to do is actually define this idea of linear. Like, why is this adjective in front of impulse momentum equation? And the reason why it's in front of it is because we're going to look at how momentum changes relative to some axis. So let's take, for example, we're going to have some particle or a ball, and it's going to be moving in this direction. And in the previous video, we defined momentum as m times v, or an object's inertia times its velocity. And we're going to say that there's another ball over here, and it has some other mass and some other velocity. And the trajectory of these particles or these balls are going to be along this line. And we could say that momentum is strictly in the direction of this dashed line. Therefore, we can say that this momentum is linear, meaning it acts along a certain axis, such as this dashed line. However, the linear impulse momentum equation can actually be applied in 2 or even 3 dimensions. So let's take another example. So let's say we have the same kind of ball, and we say that it has some velocity or momentum in this direction. And then let's take another ball or another particle, and it has some velocity in this direction. Now you can say that the momentum is acting along this axis, or this linear line, or this linear path. But what's special about this is that the momentum is not defined strictly in our typical axes, such as x and y. Rather, it's acting with respect to these type of axes, such that this horizontal arrow we'll call x prime, and this as y prime. Then we could say that the momentum is acting along this x prime direction. So although this momentum is tilted in the traditional xy Cartesian system, it is still a linear path with respect to some other axis, x prime and y prime. So in essence, what we can do is actually treat this in terms of 2 different problems, meaning this object's momentum is acting in this direction in the y direction, and this object's momentum is acting in this direction in the y direction. So that'll be one component of the momentum for both particles. And then we can say the same thing for the x direction and in this x direction. So rather, this momentum can be described in 2 different ways relative to our traditional xy Cartesian system. So although it's tilted at some angle, we could still say this is a linear momentum problem. And then you could apply this same concept in 3 dimensions. It's basically the same thing. I'm not going to do another example for that, but it's the same exact thing, that you just project the momentum vector onto the various axes, and then you have 3 different equations to solve from using the linear momentum equation. So I described what linear meant, but let me say what linear isn't. So let's take this case. Let's say we have a particle, but instead of this particle going along a straight line, it is actually curving over time. So let's take the very fundamental shape, which is going to be a circle. And we could define this point over here. So this object's momentum is actually changing with time. So this is going to be mv1, and we know that the velocity vector is tangent to the path. Therefore, sometime later, this is going to be mv2. And what we can say, this is the same thing as before. We could say that this is the momentum, but it's not linear. This is called angular momentum, and angular momentum is actually dependent on a point of rotation or an axis that the object seems to be rotating about. But it doesn't have to be with respect to this axis because it's in the center of the circle. We could define that angular momentum relative to this point over here. And in essence, this object is actually rotating, not in a very traditional sense of rotation, but it is rotating relative to this point. Therefore, we can define angular momentum in terms of this. And what I mean by angular momentum is that the object is rotating instead of going along a linear path, or an object is rotating along any given point in space. And that's what I mean by what isn't linear. What isn't linear is this idea of rotation, or angular rotation. And to be honest, this is the most general case for the momentum equation. This idea of angular momentum is the general case, and you can actually derive linear momentum by using this concept of angular momentum. But for today, we're going to strictly look at the linear case of momentum. Later on, we'll start describing angular momentum, And I'll show you how that's related to linear momentum. So now let's actually derive the linear impulse momentum equation. We're going to look at Newton's second law. What's actually surprising, what I found out the other day, is that in Isaac Newton's book, I forgot what it's called. I think it's called Mathematica or something like that, the Principles of Mathematica. I'm not too sure, but it's in Latin and so forth. But I figured out that the Newton's second law does not explicitly say that F equals ma. He just said that the force is proportional to an object's acceleration. And this idea of mass is just the proportionality constant, or in essence, the idea of inertia is the proportionality constant. But he never explicitly said that F equals ma. So that's just a modern translation of Newton's second law. I thought that was kind of interesting. So Newton's second law in today's standards is F equals ma. Force is equal to the mass times the acceleration. And what's special about this equation, as most of you might already know, is that this is a second order differential equation. And we can use this second order differential equation to come up with the linear impulse momentum equation. So in the previous video, we defined momentum as this vector equals mass times velocity. And velocity is also a vector. And this is where Newton's second law actually comes from. Newton recognized that an object's momentum changes over time due to various forces that act upon it. And if you just take time derivatives of momentum, what you get is this Newton's second law, which is a very useful equation because it's a second order differential equation that not only describes velocity, but also displacement. In essence, this is a very crucial equation that it derives a lot of fundamental physical concepts. So we're going to recognize that and derive the linear impulse momentum. I've been hyping this up a little bit too much in this video, but we're finally going to derive it. So what we can say, the first thing we're going to say is that acceleration can be written in a different way. And it can actually be written in terms of velocity, because we know that the time derivative of velocity is simply acceleration. So by knowing this fact, we're going to plug in this value into Newton's second law and solve that differential equation. So this is going to say that the force is equal to the mass times the time derivative of velocity. And this is a very simple differential equation to solve because it is separable, meaning that I could just take these differentials and multiply them on each side to get our differential equation in such a way that we could integrate it. So what I'm saying is that we could say f dt equals m dv. And we could define our limits of integration. So we're going to integrate this from some initial time to some final time. And we're going to integrate this as well in terms of some initial velocity, and these are vectors, and some final velocity. So if we focus on this side of the equation, we can actually solve that integral. So what that's going to be is going to be mv evaluated from v1 to v2. So that's going to equal mv2 minus mv1. So I'm going to take this value over here and move it onto this side of the equation. So I'm going to say mv1 plus the integral from t1 to t2 of some force f dt equals mv2, or the final momentum. And this right here is the linear impulse momentum equation. So I forgot to mention this in the video, but I just want to be extra clear that this equation depends on the velocity vectors and the force vectors, meaning that this equation is actually a combination of various equations. And since we're dealing with vectors in the real sense, such as the three-dimensional world, we're going to define these vectors in terms of x, y, and z, such that these vectors have three different components. So although this equation seems like it's only one equation, it actually composes of three different equations, such that you have the momentum in the x direction, momentum in the y direction, and momentum in the z direction. So I just wanted to be clear that this equation actually comprises of three different equations, or in other words, you have to treat momentum as a vector. And usually you have to break up that vector into its various components. So I just wanted to be extra clear about that. Don't forget that momentum is a vector. Okay, so back to the video. So let's actually dive a little bit deeper into what this is right here, this special integral. So let's take an example. So let's say we have some ball and it has some initial momentum. So that's going to be mv1. So it has some trajectory in this direction, because again, using Newton's first law, an object will stay in motion along some trajectory at a constant speed, and it won't change its direction unless some force acts upon it. So we could say that sometime later, we're going to have some force that acts upon this object. And we're going to say that's going to be F. Now this force F is actually all the external forces that act on the object. So what I'm saying is that this is going to be the sum of the forces of all the external forces acting on the object. So let's say we have some force in this direction and this force over here. So these are just the external forces acting on the object. And when you add these two external forces, what you're going to get is the sum of the external forces, which is this blue vector right here. So what we can do in this equation, we could say that this is simply the sum of all the external forces that are acting on the object. So this is just a more complete way to write this integral. It just means that you're adding up all the external forces such that the net external force is some force that is defined by this blue vector. So once that force interacts with this object, it actually changes the object's momentum. So it might look like this. So this is going to be the final momentum of the object. So this part, this integral of the linear impulse momentum equation, is what we call impulse, meaning a force acting over some given amount of time that actually changes an object's momentum, as you see in this picture. So that's what this integral is. This is called the impulse. In a future video, I'm going to go a little bit more deeper into what impulse really is and what forces are actually considered impulse. So if you're still a little confused on that, I'll go through that in a future video. And then the other parts in this equation is the initial momentum and final momentum. So that would be just simply the momentum here and the momentum over here. Now let's say what if we say that T1 from T2, the sum of the external forces over some given time equals 0. So if we say that the sum of the forces equals 0, meaning there's no external forces acting upon it, the momentum will be conserved such that its momentum will still continue along this line. So this is mv2. I'll say prime. The prime is not derivative. I'm just trying to distinguish between the momentum from this momentum over here. So what that means is that the initial momentum v1 equals mv2. So if we let the impulse equal 0, or say there's no external forces acting upon it, then we can say that momentum is conserved. So this equation right here is actually known as the conservation of momentum. So we can say that momentum is conserved when there's no external forces acting on the system or the free body diagram or the particle that we're looking at. So that is what is meant by this equation. So you can see that this path right here is when momentum isn't conserved because there's some external force acting upon it. However, if there's no external forces acting upon it, then we could say that momentum is conserved. And that's because there's no unbalanced force that is going to change an object's momentum. And you might be saying, why is this even useful? I mean, that seems kind of intuitive. Like, why does it even matter to even state this? Because that seems obvious, because this is already predefined in Newton's first law. Well, that's actually a good question, because momentum can actually be transferred to different particles in a system of particles. So let's say we have some particle and then some particle over here. If this object is initially moving and this object isn't moving, then when these objects collide, momentum is actually going to be transferred to this particle, which is actually going to make it move quite a bit, and this particle is going to move in maybe in this direction after they collide. So when this equation can be applied to a system of particles instead of just one particle. And I do agree, if you only look at one particle or one body, this equation is trivial. But if you look at a system of particles, then the equation becomes more and more useful. And we'll talk about momentum of systems of particles later on. But the main concept of this video is to come up with this equation of the linear impulse momentum and the special case when the impulse is actually equal to 0, which is the conservation of momentum. So that's what's behind this idea of linear momentum. In the next video, we'll talk a little bit more about impulse and what it actually means, what kind of forces are actually considered impulse, and what forces aren't actually considered impulse. So in the next video, we'll go over that topic a little bit further. But the main idea, again, is just to understand this equation right here. So with that being said, I'll see you in the next video.